So the next thing I want to discuss is a very important topic, which is propagators and boundary conditions. Or I should say propagators, causality, and boundary conditions. So above, what we showed was that if x and y was space-like separated, then this thing vanished. Now let's look at the vacuum expectation value of this commutator. So the vacuum expectation value of this commutator, since we know what the commutator is dk tilde e to the power minus I k x minus I minus e to the power minus I k y minus x times the bracket of the vacuum, which we can assume to be normalized, and that's equals to 1. Now these two terms, we can rewrite them in a slightly different form. And so the first guy is e to the power minus I k x minus y. And then, what we can do is that we can now write the dk tilde as d cubed k divided by 2 pi cubed. And then we can write the 2ek as a denominator here. And what we are saying is that the k0, if you look at a four-dimensional vector k0, of course, its zeroth element is given by ek. And then we have, as a second term, we can write e to the power minus I k to the power x minus y, and divided by minus of 2ek. And here we take the zeroth element of k to be minus ek. So let's pause and figure this out. So what's happening here is that the k0 element is being put, has a negative, is a negative number. So what we would get is that then this, for the k0 element, this sign would flip and it would become positive k0. And then the positive, so we will have plus I k0 x0 minus y0, which is exactly what this is over here. So here, we have switched y and x. But on the other hand, the 3 part of this integral, of this exponential, that actually differs by a sign from this thing. And the way to justify it is that the 3-dimensional k integral is actually invariant under k going to minus k. So we can do that substitution in the second integral to write it like that. So once we've written these two terms in this way, what we can do is that we can write this as a contour integral, a 4-dimensional contour integral. So we have d4 of k, and here we get 2 pi cubed. And let me just put d cubed here and put another integral now over dk0. So, and here's a 2 pi. And then we'll have here minus e to the power minus I k x minus y divided by k squared minus m squared. So what's happening here is that, and this is a contour integral. The zeroth integral is an integral over the contour gamma. So what is happening here is that we see that this thing has on the k0 in plane. So if I take the k0 plane, integrands have pole at e equal to plus of ek, and E equals to minus of EK. And so the contour that we have to take is the following. We go this way and we go over these poles, and we go here and we go over this. And now what we have to do is that we have two choices. We can either close this contour in the lower half plane or go and close it on the upper half plane. But whether we can close it on the lower half plane or the upper half plane will depend on the sign of this argument of this exponential, because we want this contour integral to be equal to this integral such that I get this result. And so we see that we'll have two choices. One is when x0 is greater than y0. When x0 is greater than y0, what we can see is that here, if you look at the imaginary part of k, it's only when the imaginary part of k is negative, that's when the integral will vanish on this part of the contour in the limit where the radius of this semicircle goes to infinity. So in other words, for this case, we are doing a contour integral where we have the two poles here, and then the integral goes like this. It goes over, and then it closes on the lower half plane. And we take this radius to go to infinity, and these small radius, say small r, those go to 0. And in that limit, we get a non-zero result because our contour is now includes these two poles, so we have to take into consideration the residues of this pole. On the other hand, when x naught is less than y naught, we see that this exponential factor decays only in the upper half plane. So in that case, the integral that we have to do has to have the form of, so we have the poles here, and the contour we have to take has to go like this, and then it has to be close on the upper half plane. And we take the limit where r goes to infinity, and the small r's go to 0. If we do this, we see that our contour on the upper half plane does not include any poles, and therefore the result of that contour is going to be 0. And therefore, when x0 is less than y0, our integral gives us the value 0, which is exactly the boundary condition that we expect. So we want, so basically what we are doing here is that we are choosing the contour in such a way that the function, let me call this function d of r. This function d of r is non-zero when x is in the future of y, and it is 0 when x is in the past of y. So this kind of propagators are called retarded propagators. Retarded propagators, and that's because in these propagators, what happens is that the influence from y propagates to x only if x is in the future. These are also called causal propagators. Well, there are other causal propagators, but this is known as the retarded propagator. So one way of writing this to encode the boundary condition is to write d of r x minus y to be equal to theta. So theta is the Heaviside theta function, which is non-zero when the argument is positive, times the vacuum expectation value of the commutator of x and y, like this. So this is the retarded propagator. Now, you should realize that intuitively, if we had chosen different contours, then we could have influenced, we could have other kinds of propagators. So for example, there are propagators, their functional forms will be different, where for x greater than y0, the contour will not close below, but it'll close above. And in that case, in this case, if the pole structure were the same, then the propagator would be 0 for this case. Whereas, for x0 less than y0, the pole, the semicircle would close below. And in that case, if the function had the same pole structure, the propagator would be non-zero. So in that case, we would have a propagator where the influence propagated from the present into the past. And such propagators are called advanced propagators.